All right. So in the last class, we had discussed about this idea of single input and single output systems, and then multiple input and multiple output systems. How can we control such systems? And we were talking primarily about a heading autopilot for a marine craft. We were looking at what were its basic components. We looked at the idea that it consists of a control system, a control allocation, then a reference model, a compass and a yaw rate sensors, and then a state estimator with wave filters, and then finally a wind feed forward term in case if we want to compensate for the wind. So these were the topics which we kind of broadly covered as to what are there in a heading autopilot. Let's put all the pieces together today. So it's like we have looked at these individual pieces of these jigsaw puzzles, some in guidance, some in control. Let's put them all together today in one place, and we'll try to see how it all fits together. Okay. There is one piece of the puzzle which we have not discussed as yet, which is the state estimation, which we will discuss in a little bit time. But up till now, whatever we have discussed with respect to guidance and control, let's put them all together in one place. Okay, so the main idea of this heading autopilot is that it should have a reference model, and which must be able to have both course keeping and turning a bit capabilities should be present. So we are not just interested in keeping a same course, but we also are interested in, if we want to change the course, how should that go about? So it should provide us with a desired heading angle, desired yaw rate, and the desired acceleration of the yaw rate. These quantities should be provided by our so-called reference model. So if an operator input is provided to it, these reference models will give out the desired values of these outputs. Then our control system will try to track those desired values. So these typically we saw that there are different ways to obtain them, and one of the ways which we had discussed early on in the guidance system formulation was if we looked at low pass filters to be generating these signals, which are relatively slowly varying with time and hence can be followed by your craft dynamics. So we'll try to take a quick recap on that. So here we will assume that the heading angle, the desired heading angle, is controlled by the desired operator input which we provide, and that is governed by a third order filter, which you can see here was taken as cascade of a second order filter and a first order filter. So we have the first order filter as S plus omega n, and that conjugated with a second order filter, which was 2 zeta omega n s plus omega n square. The main idea here is that we get to choose our damping ratios and natural frequencies as we desire. So depending on them, the signal will be as slowly varying or as fastly varying depending on our requirement. And depending on the craft that you're trying to actually apply this to, you may want to choose your omega n and zeta values accordingly. We also observed that with this what you call third order filter, it ensures that in the steady state, the value of the desired output is actually equal to the reference output, and that can be seen here from your transfer function, where I can say that psi d is equal to this entire thing times psi r, and if psi r is a step input, I can write it as sum psi r0 by s. So the limiting value of psi d is then given by limit s tends to 0, s times whatever we had here, and then it is easy to see that this s and this s will cancel out, and whatever we have here will be the ones which will be left. So s plus omega n, and then that whole term here. So once I apply the limit s tends to 0, you will see that this reduces actually to psi r0, which means whatever step input I gave, that is the output I'll come out with it as time tends to infinity. Okay, So that's fairly evident here. Even if you wanted to formulate the differential equation corresponding to this and see that all the higher order derivatives are going to zero, you will still see the same aspect come out of the picture. Okay. Everybody with me so far on this? Yes, no? Yes. Okay. All right. So notice that in this approach, when we try to compute our psi d, psi dot and psi double dot are also smooth, and that is why we went for a third order filter, so that even psi double dot is smooth enough. Okay. If we only went for a second order filter, then we might have seen some discontinuity, not a discontinuity, but a non-differentiability in psi dot possibly, psi double dot possibly happening. But by using a third order filter, we are ensuring that if at all there is any non-differentiableness, which means that will only happen in the third derivative of psi. So we are not really interested in that. We are able to get a smooth values for psi d, psi dot d, and psi double dot d. All three of them, we are able to get a smooth estimate using this third order filter. As we have seen before, and probably even yesterday during some of our tests, saturation is an important aspect to keep things practical. Otherwise, you may be going crazy. So therefore, it is important to limit the yaw rates and the accelerations to some maximum value so as to have some practical relevance. So in this sense, the resulting system, the third order system, can be described as shown here. So we have psi d dot is equal to saturated value of RD. RD dot is saturated value of AD, and AD dot is given by the actual third order system which you are seeing here. Okay, so that is the differential equation which is governing our system. And here we are simply basing the idea that the reference value being provided is getting converted into the so-called desired yaw trajectories. Okay, we are here only looking at the yaw trajectories in using this so-called third order filter, which we have chosen as our guidance system. The main idea behind using these filters is that they are relatively simple to program and they are not complex in the terms of computation effort which is required. So they can be easily be implemented on any vehicle. Again, saturation basically means that as if I plot the saturated value of x versus x, it's a linear line as long as the value reaches some x max, and then it stays constant at x max from there. So this is x max minus, and this is x max. Okay, so that's what a saturation signal means. Mathematically, I can just denote it as you're seeing here as a case basis function. Now, this simple third order filter system is a good method, but sometimes we may be interested in more sophisticated methods to generate the heading reference angles, and that can be seen. We have seen some of these examples in terms of line of sight based algorithms. Okay, so we'll try to come back to that idea as to why that is important, especially if we want to do a position tracking as well. Okay, so far we are looking at the heading autopilot only. So therefore, a good reference signal for the autopilot can be a third order system. But if you want to do position tracking, where you have certain waypoints and you have to make sure that your vehicle follows the path between the waypoints, then you have to start wondering about a better guidance algorithm rather than a simple heading control algorithm. And we'll see that also today as to where that is tying into the picture. So the moment now, if we are talking only, so we are still focused currently about the autopilot system, which means we are only trying to control our heading, then the PID control law can be formulated for our simple Nomotos model, and that simple Nomotos model can be formulated as you see here, a simple single degree of freedom yaw equation of motion, where you have the inertia terms in the yaw. So this is the mass moment of inertia, this is the added mass, times r dot minus nr times r. So this is the damping term. and that is equal to the external forcing. The external forcing can be coming due to two aspects. One could be due to the wind, and the other is due to the effect of your controllers. So the moment I apply a rudder, there will be some thrust which will be generated. So this is a very simplistic model, but gets the job done for most of the cases when we are looking at a heading autopilot being operated in the open ocean. So if I define this Iz minus nr dot as m and minus nr as b, so representing mass and damping, we have seen this before that we can specify this so-called time constant t as m by d, and that will result in me writing out this equation in a slightly different form in terms of m and t. So r dot plus 1 by t times r becomes 1 by m times tau wind plus tau n. So now the idea here is that this tau n, which is the control input which we are needing to be provided, can be specified in terms of the different actuators which are present. If it's a single screw ship, then that tau n simply becomes n delta times delta, where we are primarily depending on the rudder angle. But suppose I have more number of inputs than a single rudder. So let's say I have a bow thruster and I have azimuthing thrusters which the ship is equipped with. Then I may have multiple actuators. So let's say that I have R actuators. So I can put them all in a vector and I can find out what is the torque which I'm generating or the moment that I'm generating. That is equal to some thrust allocation matrix B transpose times U. Okay. In this particular case, it will be scalar because tau n is scalar, so therefore B has to be a single dimensional vector. Okay. Otherwise, if tau was a generalized force vector, then this could be a matrix. So B could be a matrix in that case. Okay. So assuming that we know what the heading angle and the yaw rate are, and assuming that they are being measured in some sense using either a compass or a gyroscope or an attitude reference system of sorts, we will be able to formulate our control law, which defines what this value of tau n should be, and we can write that as minus tau wind estimated. So this is the feed forward term for the wind. So we are basically dynamically trying to cancel out the wind effect even before it makes a change in my heading. And then you have some tau feed forward. We'll talk about this in just a minute. And then we have our regular PID controller, tau PID. Okay. So the idea here being that we are taking the error between the desired heading and the actual heading and using that in our PID control law in order to come up with the amount of moment required to keep my ship back on track with whatever original heading that I wanted to follow. Notice here that psi tilde here, which I am representing here, is nothing but the difference between the actual heading angle and the desired heading angle, where the desired heading angle came from my third order filter. Okay, that's where we are right now. We'll relax that condition a little bit in just a second. All right. Okay, as I said, this tau wind hat, which you see, is an estimate of the wind moment, tau wind. So we may not precisely know what this exact tau wind is. So we are making our best guess estimate of what that tau wind might be. And we are trying to feed forward it into our control law so that that can be compensated for. And this estimate is derived using the fact that we have some sensors for the wind, which are able to measure the wind speed and wind direction. And based on that and the geometry of the hull form that we know, we will be able to estimate what should be the moment which should come onto the wind. And we have seen this before. It can be described in these terms: half rho A times VRW square times some wind coefficient Cn, which depends on the relative wind direction gamma RW times the projected area, lateral projected area times the length. And we have seen this before when we were looking at the environmental modeling for the wind. So I'm not going to go much in detail. This is just to put everything together at one place so that we can appreciate what is going on. So the idea now is that this VRW was taken as square root of small URW square plus small VRW square, where these are the relative directions in terms of the uh, with respect to the ship's body fixed coordinate system, what is the wind speed, relative wind speed. And that is how they are defined. They are defined as the speed of the vessel minus the wind direction in the surge, speed of the vessel in the sway minus the wind direction in the sway. Okay, one important thing which you must keep in mind when we are trying to implement this tau feed forward is that wind measurements must be low pass filtered to avoid rapid changes in heading command. So we want to make sure that these very high frequency stuff or very quick changes in wind are not compensated for, because that will only make our actuators wear out much more quicker. So we want to make sure that only the slowly varying forces or the drift forces are being taken care of. Rather, the high frequency stuff should be avoided. So what we can do is we can take these wind measurements, pass them through a low pass filter, and then use those values in order to predict our estimated tau wind hat, right? So that way we are all able to compensate only for the slowly varying components, and any small variations here and there, they are not going to affect us much, but we are able to disregard them in our control room. We'll talk a little bit about this feed forward methodology which we have put in place. So basically, if you look back at our equations of motion, so we have tau wind plus tau n. So if tau n is equal to minus tau wind, basically I'm just compensating for that wind altogether, right? Then I know that my system will stabilize in R. Okay, in case that there are no other disturbance other than wind, then a simple application of the tau feed forward wind will allow me to compensate for the wind dynamics. That is the main idea behind it. But since we were providing a PID controller, one might have thought, do I really need this feed forward? Can't my integrator take care of it? Okay, and the idea is yes, your integrator was there to take care of these things only. It was there to take care of these so-called steady state disturbances. So why not use that? Why should I use this wind feed forward methodology? The main difference comes in how quickly that the system responds. The wind feed forward is basically saying that, okay, I'm experiencing so much amount of wind in so and so direction right now, which is going to result in a wind force of so and so. So let me compensate for it right away. Okay. Whereas the feedback system, which is your integrator, it will only come into the picture once your error has accumulated to a larger value, and that error term will now start to push the ship back into the correct heading. So it has to deviate from its current heading, and then it has to come back. So the response time is more for your integral action. Not that your integral action can't take care of this steady state disturbance, it can, but the response time will be larger. Whereas if you use a wind feed forward model, then you are basically compensating for that ahead of time. Before the force can push you off, you are applying a reverse force so as to keep in place. Right? It's more reactive in nature rather than the feedback system where I have already experienced a large error and then I am trying to compensate for it. So in that sense, this feed forward is faster than integral action. And typically when you start up, the integral term takes several minutes during the startup to compensate for large wind components. An example of this was yesterday's experiment, where we saw that when you started off, it took a long time for the integrator to slowly start picking up values and slowly start increasing your value of the control input which you are providing. Right? So it takes a sufficient amount of time for it to actually start stabilizing at a particular level. So that can be avoided if we have a feed forward mechanism. Now, the integral action typically works well when we are looking at a fixed heading or a station keeping problem or a transit problem where the heading angle has to be kept constant. But if I'm looking at problems where my course is changing quite a bit, and let's say that my heading angle has to undergo a big change, then this integrator term can cause a lot of problems. This integrator basically can accumulate error over time and really become a large value. And that is what is called as integral windup. Okay, and once that value has become sufficiently large, what happens due to that is when I now change my course, I start seeing large overshoots come up. Yes, it will come and stabilize back to the same value where I want to stabilize, but there will be a large overshoot first, and only then it will slowly come back and stabilize to the point where it wants to stabilize. So integrator, you can think of it, is a destabilizing component of that control law. So whenever we have something as an integrator being added to a control law, it will have destabilizing effect. And we have seen this before also. Remember, in the multiple input, multiple output system, with the PD control, we were able to prove global asymptotic stability, but the moment we added the integrator, we could only show local asymptotic stability. So whenever we are adding an integrator to the control system, yes, it has its advantages that we'll get our steady state error to 0, but it does create stability problems many of the times. Okay, so that can be a serious issue when you're looking at integral action to compensate for winds. So in that sense, it is advantageous to implement a wind feed forward, because that reduces the that takes the pressure off of the integral term to compensate for these disturbances, but I'm trying to compensate for them ahead of time in some sense. So we can get a much better performance when we are having a startup value. When we start off our station keeping problem, let us say, a wind feed forward can help us keep the integrator values relatively lower so that the performance can be guaranteed to be much better for a longer duration of time. Whereas the method does have a caveat that if you do not know your wind coefficients precisely, okay, let us say I don't know my wind coefficients really well, then that estimated value of wind force will not match the value of actual wind force. And then the integrated term will have to take into account that error. Okay, so this method can have some problems if we don't know what the precise wind coefficients are. So if we know the wind coefficient somewhat reasonably well, we can use this method so that the load can be taken off of the integrator, but otherwise the integrator will still have to do the job. Okay, so if I want to look at this entire thing in a continuous time representation sense, after I put everything together, so previously we looked at it in the Laplace domain, let me try to specify it in terms of a continuous time, what's happening. So we'll have our total control torque is E, or moment, is equal to minus of the wind feed forward term. This feed forward term, I'm yet to talk about this. I'm going to talk about this in just a bit. Minus Kp times SSA, which is that small sine angle, which is that we are looking at, if we are taking a difference between two angles, we want to look at the smallest angle between them, rather than seeing a jump when it starts to cross 2 pi value. Okay, so that small sine angle of the error between the actual heading and the desired value of the heading. So we're trying to see what is the small sine angle of this, minus Kd times R tilde, where R tilde is R minus R desired, assuming that the desired is here varying with time. Okay, so I'm presuming here that the desired value of Rd will vary with time. And then we have our integral term, Ki times integral 0 to t, small sine angle of the error, integrated over time from 0 to t. Now, these controller gains can be tuned using the pole placement algorithm. So we have seen that before, where we specify a bandwidth value, and from the bandwidth value we can figure out what is the natural frequency of the system, and once we specify the damping ratios, we can actually precisely figure out what should be our gains, Kp, Kd and Ki, so that the poles of the system are located exactly where I want them to be located. Typically, for most marine crafts, you would choose this zeta value to be between 0.8 to 1. So it is kind of close to critically damped case. You would want to keep it there. So therefore, really what you can play around with is the bandwidth, right? So the main design parameter as a control engineer that you can play around with is the bandwidth. And that bandwidth can be taken to be approximately for large tankers to be about 0.01 radians per second, for smaller ships to be zero point 0.1 radians per second. But then again, these are just thumb rule values. It's not a one size fit all. It's just giving you some representative numbers to start off with, but then you'll have to tune them properly so that your performance is matching with what you want it to match with. Okay, so with that caveat in mind, we can kind of see that omega b, or this bandwidth value, is what we play around with in order to determine these gains, and then those gains are basically giving me the control law, and that will try to compensate for my heading angles. Is everybody with me so far? So we have looked at this autopilot system in terms of there is a guidance algorithm which is coming from a low pass filter, which is giving me the desired states. And then I have a controller part, which is taking a PID control strategy in order to compensate for the differences in heading error. We looked also at the idea that the controller can include this so-called feed forward term of the wind, where we are trying to compensate for the wind gusts which might be coming into the picture. So if we tune everything properly, the idea then becomes that we are able to track our heading is able to track the angle which we specified, okay, through our reference output. Whatever the operator has given, that translates into a desired heading angle, and that desired heading angle is now tracked by your actual heading angle. So at the end of the day, whatever is the operator specifying as the heading angle, you have reached that heading angle if you have tuned the gains appropriately. Notice that all of this estimates work really well only when this n is known really well. But for most cases, we can know this m precisely well because it's only the mass moment of inertia minus the added mass moment. And since if the geometry is known well, we can predict these two quantities pretty well. And the weight distribution is known, we can predict these two quantities fairly well. Okay, so once we have that tau n, so far we talked about the idea that psi r is translated into psi d, and then what is the tau n needed to bring psi d and psi to match together, right? It's in fact the other way around. Psi needs to match psi d. I need to apply a moment tau n. So that is what we have looked at so far, where the tau n is coming from our PID controller. But typically, as I said, you have to have an allocation problem along with it, which means that once I know what is the moment I want to apply, I have to break it down into how much actuator input do I need to give. What is the rudder angle which I need to specify? And in case of a rudder, simply a single rudder controlled craft, this is fairly straightforward. But if you have several actuators, then in that case, you can take the value of these actuators as B times B transpose times B inverse times tau n. This is called as the generalized inverse, basically where I am able to take an inverse and then, because this is a vector valued function. So remember that originally we had tau n being defined as some B transpose times U, right? Where B was some vector and U was some vector. Now, since B is not a square matrix, I can't just take B transpose inverse in order to find out what will be U. So I have to go with a so-called generalized transpose method, which is what you're seeing here. Basically, if you substitute this B transpose U into here, you will see that this basically becomes B times B transpose divided by the scalar value, which is non-zero. That's what it is doing. Okay. Everybody with me so far? All right. Let's now talk about that so-called feed-forward term, which I did not speak about. So remember back in our this thing, there is this feed-forward term, which I have introduced into this control law. And I told you that we're going to talk about what that means. What does that do? What that feed-forward term is basically doing, it is allowing me to obtain a perfect tracking during the course changing maneuvers. So as my course is changing, it is trying to allow me to have a perfect tracking during the course changing. What it means is that I'm assuming that this so-called desired uh, heading angle, psi d, it has a dynamics which is given by some Nomothos model, and I'm putting this feed-forward model as m times rd dot plus 1 by t times rd. So what is that doing? By putting this into our original control system, so our plant was looking as r dot plus 1 by t times r is 1 by m times tau, right? Assuming that there is no wind specifically right now. Okay. In the absence of a wind, this was our equation of motion. Correct? Everybody with me so far? Now, what I'm saying is, if this tau n, I'm specifying it as m times rd dot plus 1 by t times r dot, what will happen to this? It will become r dot plus 1 by t times r is equal to rd dot plus 1 by t times rd. Correct? So if I define that so-called error between the actual yaw rate and the desired yaw rate as r minus rd dot, then you can see that that error can be, there's a mistake here. No, this is fine. Yeah, so I'm specifying error as psi minus psi d. So then E dot is basically R minus RD, and E double dot is R dot minus RD dot. So using these three terms, I can see that this equation can be represented as this. Correct? Okay, assuming the right hand side is 0 there. Okay, assuming that there is no control action, then I should get that this will translate to the fact that E double dot plus 1 by t times E dot is equal to 0. And as long as t is greater than 0, this means that the system is exponentially stable. Yes. As long as t is greater than 0, E double dot plus 1 by t times E dot is equal to 0 will have an exponentially stable system. Solutions will converge exponentially to E equal to 0. Okay, so I'm able to say that by applying this so-called feed-forward model, I'm able to kind of ensure that this error term tracks and exponentially the 0 point. Now, if there is some further error beyond that, that my PID law can take care of, and that is why that extra term which I'm putting here is the PID controller. So the idea here is simply that I want to kind of make my PID get into action only when things are going haywire, like when there is a disturbance due to wind, wave, or currents, only then it should be activated. Otherwise, my control law can basically take care of itself that the error goes to 0. Okay, so rather than use my Kp and Kd to compensate and bring my error down to 0, I'm having this so-called wind feed forward law, which is described in terms of Rd and Rd dot, which will allow my system to naturally progress towards E equal to being 0. Okay. Now, if I add disturbances and other things, then my PID law can take care of that. So the load is now distributed primarily. The PID is only looking at when the errors are coming into picture due to environmental disturbances, that it will become active. Otherwise, this control law should take care of it. Everybody with me so far? Okay. I'm not doing anything. I mean, I could have put this as a part of my PID law as well, and it would still have worked. I'm just trying to separate out the components so that I can specify which part is controlling what. Everybody okay with this idea? Yes, Anand.
Sir, how does the system know when to activate the PID controller, sir? Like,
Sorry?
how does the system know when to activate the PID controller? You told that PID works only after some
No,
overshoots.
no, no, because the PID control law, tau PID, we already saw that it is specified in terms of these things, right? It's specified in terms of the error in psi error in RD, and error in the integral value of the error. Right? So whenever the desired values, you deviate from the desired heading angles, right? Automatically the PID law will have non-zero coefficients there, which will try to push the error back to zero. My only point was that instead of trying to make sure that the system will go to a zero error using the PID control law, I'm stating that I'll provide a feed-forward term such that naturally the system dynamics will always tend to zero in the absence of any external disturbance. If there is any other external disturbance which is coming into the picture and trying to push my craft away from the heading that I desire to track, then the PID will compensate for that difference. Ideally, this also is a part of your PID as well. You can think of this as a constant term which you're adding with your PID law.
So it's this feed forward thing is only for wind or for all external forces?
No, no, no. This feed forward thing is not for the wind. Wind feed forward we discuss separately, where we estimate the wind force and we are compensating for that, correct?
Yes.
So
So what is this?
we are adding that feed forward thing already there. I'm saying that in the so this PID control law can be separated into two parts. You can just think of it in that way. Okay, the PID control law itself, let's say it is separated into two parts. One part which naturally drives the error down to zero, and the second part is in case there are any external disturbances, those will be taken care of by the secondary component. It's not different. I mean, you see, technically what is happening, this tau feed forward, what is that? M times RD dot plus 1 M by T times RD, correct? I can combine these terms into here, right? This and this. I can basically combine these terms here. Seeing the point?
Yes.
Okay. The main idea is that I'm trying to separate my control law into two portions. I'm saying that one portion will naturally try to push the dynamics to be E equal to 0. So E equal to 0 becomes globally exponentially stable. And then I have, if there are any other disturbances which are coming into my system, then the PID will take care of that. This is particularly important for course changing maneuvers because you see that this term M times RD dot is not there anywhere in your regular PID term. You can't put it anywhere in your regular PID terms. Right? So if I have a changing course and I want to make sure that the system is stably tracking that, then I'm using this feed forward term to ensure that in the absence of any disturbances, naturally the system will try to go reach the path that I want it to follow. Everybody with me so far? Okay. In addition to that, if there are now any disturbances coming into the picture, then those disturbances can be accounted for using the PID term. If there is any steady state disturbances, those will be taken up by our PID control and it will try to compensate for it. Okay. It's just a staggering part. It is trying to ensure that the control part, what it is doing, I'm kind of trying to separate the different components that it is trying to compensate for. One component is wind, one component is it is trying to make sure that the error goes to 0, and then there is the third component which is trying to take care of if there are any steady state errors, any environmental disturbances, they will be accounted for by my PID law. Okay. It's as if the same controller, I'm just breaking it apart to see what do I need to put, so that which component is accounting for what. Okay. I'm basically opening the toolbox and seeing what's going on there inside it. Okay. Is that clear, or shall we go over it one more time? Is there some further things which are bothering you guys?
Clear.
Clear for everyone? Shadab?
Yes, sir, it's clear.
It's clear. Okay. All right. So then let's go ahead. So in this case, then you can see that basically what is happening is that if I want to look at this system, which I get after application of this feed forward law into place, then my error dynamics is given as E double dot plus 1 by T times E dot is 1 by M times tau PID, right? So if I now think of this tau PID as a input which is trying to drive my error, it's a differential equation where an input is my tau PID and the output is the error. Correct? Now we know that tau PID itself is actually depending back on error again. It's like a closed loop thing, right? I have the plant dynamics coming in, and then I have the basically I have the controller basically. This is how it is looking, right? The controller is basically looking at what is the plant doing, and then accordingly taking the error between the reference value and the what it is doing, and then using that error to generate the so-called thrust vector, right? And that thrust vector is being applied, so that tau PID is being applied to the plant, and the plant basically will generate the error back. Right? That's what is happening. So if I just think of this system and see as to what is the transfer function for this system between E to tau PID, I can kind of write that down as here, right? E by tau PID will be P by M divided by S times Ts plus 1. Is this clear for everyone?
Yes, sir.
I'm just taking a Laplace transform of it. That's all I'm doing. Okay. Now, I do know that actually this tau PID is actually some function of the error, and that basically is Kp times error, Kd times the derivative of the error, and Ki times the integral of the error. So if I want to write that in the Laplace transform part, I can write that transfer function between tau PID to the error as this transfer function which you see here. Is that making sense? Yes, no?
So, sir, since tau PID is a function of the error itself, we are converting this into Kp into what plus TDS. Yes.
Correct. So this thing is nothing but, if you look back in our PID control law, it is depending on this error, right? This is E. This is E dot. And this is integral of E, right?
Yes.
So basically, if I write what that tau PID is as a function of E in a Laplace domain, I can write it out as this fellow right here, where basically Kp times Td is Kd and Kp by Ti is nothing but Ki. That's what it means, right? A typical PID controller. So what is happening, I'm kind of trying to understand this so-called loop of the system. Is it stable or not is what I want to figure out. So given some error, right, the PID will generate some torque, some moment, and given that moment will result in some error. It's a closed loop system. It's keep on going in continuously. But I want to kind of break that loop at some point and observe. If I give an input amplitude of 1, what I get back, is it greater than 1 or less than 1? That will tell me whether the system is amplifying my errors or is it decaying my errors. In that sense, to understand this stability, I want to look at that so-called loop transfer function, which is nothing but a cascade of these two fellows, right? I actually have h of s, which is E by tau PID, and h PID, which is nothing but tau PID to E. But I have cut that loop, and I'm just trying to see, given a certain signal input, what do I get back? Everybody with me so far? So I want to see whether the system is going to amplify my errors or is it going to, what is it going to do? Is it stable enough or not? So from a stability point of view, I am really interested in this so-called loop transfer function L of S. And this loop transfer function is what will define when my system is stable and when my system is becoming unstable. Okay, so in order to figure that out, this becomes my loop transfer function based on which we can actually calculate stability properties. As to when is the value greater than 1, for what frequencies is the value greater than 1, or for what frequencies is the value less than 1, meaning that it is actually getting attenuated. Okay. And basically this loop transfer function will also define what is my bandwidth of the system. You remember precisely, the bandwidth is specified in terms of what is happening to the loop transfer function. Where the loop transfer function reaches its value of 1 by square root 2, that is the value which we specify as the bandwidth of the system. Okay. So in that sense, if we wanted to investigate stability, this becomes my so-called loop transfer function for the combined PID system. Okay, so what we have looked at so far is basically we have looked at a heading autopilot, where we have looked at a guidance system for a heading autopilot, which gives me which takes as an input a reference value from the operator, gives out a heading angle which is desired heading angle. And then we looked at a controller which is trying to say that, okay, I want to make sure my actual heading angle is making sure that it is tracking the desired heading angle using a PID controller. In addition to that, we saw that there are two more terms which we have included. One is the wind feed forward term, and the other is a feed forward term which we want to make sure that the trajectory is naturally globally exponentially stable. Okay, so that completes our loop. And notice here, as I said, when we went through the process, I mentioned neatly somewhere in between. I don't know how many of you noticed that we said that a psi and r are measured using some compass or something. So we know what those values are. We are presuming that we precisely know the heading angle and we precisely know the yaw rates of the actual system. So only when I know them, I can do the feedback. Otherwise, how can I do the feedback, right? So assuming that I know these, we have talked about the control system and the guidance system, how they can work together in this case in order to make sure that the heading is tracking a desired heading that I want to track. But I can now try to go a step further. So remember that our original discussion when we started off this control systems, we talked about this idea of successive loop closure, right? So we can now talk about that, where now the heading is matching, but I want it to go through certain waypoints. Then I can try to change that guidance system slightly. Rather than using a third order filter, I can feed that guidance system a desired heading angle from my LOS guidance scheme. And that is what we'll look at next. I'm just trying to, we have looked at all of these individually, these components individually. We are trying to put them all together in one place and see how they would work. So, in some sense, we were looking at this so-called inner loop dynamics, where this control system was getting some value as input from a guidance algorithm, which was providing me the value of psi d. And then this control system was basically looking at a wind feed forward and a control allocation in order to figure out what will be the delta, and that would work with the plant along with the wind forces to generate some heading angles. And that heading angle is being measured through your sensors and is being passed back to the control system. And that is what we have looked at the architecture so far. Okay, where this heading angle, desired heading angle, was coming from a third order filter. In the previous example, that is where the third order filter was feeding me these values based on an operator input. Now we will see the idea that if I want to do position tracking as well, path following as well, then I can close the loop outside of this inner loop. Okay, where I'm trying to say that the heading angle, the desired heading angle, will now come from a LOS guidance scheme. Okay, and then basically the plant will generate its heading angles, which is going back into the inner loop is okay and fine. But I'm also interested in the positions of the actual vessel with respect to the waypoints which I specified. And then I look at that output and feed that back into my LOS algorithm. So this is an outer loop which I'm closing outside of this inner loop. Okay, and that outer loop is kind of being closed by the guidance system rather than by the control system. Okay, and that guidance loop will basically ensure that my system is now X and Y are tracking or passing through the waypoints which I have specified. Xn and Yn I, and I can be ranging from some 1 to capital N. So if I have specified n waypoints, one after the other, it should start tracking one after each of them. And the mechanism for my changing of this guidance law would be specified in terms of my desired heading angle will be specified by pi p minus tan inverse of kp times ype, where this is the cross track error, minus beta c, where this is the crab angle. Okay, now ideally what we want to do is we probably will not be able to compensate for the crab angle. So we can think of it as an unmodeled dynamics, and we can simply put an integrator, and we have seen that aspect when we do integral line of sight algorithm, where it can be made stable enough. So the idea then becomes psi d is simply given by pi p minus tan inverse of kp times ype plus ki times yp int. Okay, where yp int is basically being governed by this dynamics, which will ensure that the system is uniformly semi-globally exponentially stable. We had looked at this aspect when we were discussing guidance systems. So by putting that together, we are able to figure out these psi d values will be now fed in to our controller, and the controller will basically try to make sure that the actual heading matches this desired heading. So that inside loop will make sure that psi d is equal to psi, and the outside loop will try to make sure that the psi d is controlled such that we track the path which is provided between the two waypoints. Okay, that is the main idea behind it. Again, here we should have a mechanism for switching the waypoints, and one of the easiest ones is once you are within a circle of certain waypoint, you should start tracking that waypoint. As and when you reach another circle of representing the next waypoint, you are inside of that, you should start tracking that waypoint. So that is one of the easiest methods to switch between the waypoints. And we looked at a couple of other approaches as well. This is just the one I have specified here for the sake of completeness. More detailed discussion we have already had on that. So what we have essentially looked at today is we have kind of put everything that we have learned together in the guidance systems and the control systems all into one place. Okay, we have looked at the idea that the heading controller will take in an inside loop dynamics where the heading angle, the desired heading angle is coming from an LOS guidance scheme, and the inside loop is basically trying to correct for the fact that there is an error between the desired heading and the actual heading, and it's trying to drive that down to zero using a PID controller. But that heading itself is being closed by an outside loop where we are trying to make sure that that heading is given in such a way that I start tracking the path between two waypoints. You can even extend this further. You can even say that these waypoints need not be having a straight line path, in which case we would be looking at our curved path LOS, which we discussed in our guidance systems. But the only challenge is the more you are going into these curved path and other things, you have more computational overhead to solve for the desired heading angle rather than in the straight line case where it is fairly easy to figure out what that value is. Okay, is everybody with me? Has it kind of all come together into one jigsaw puzzle? That was the aim of today's lecture, that whatever we have discussed in the guidance and control should all come into one jigsaw puzzle. And what we'll do is our next assignment, we'll try to focus on this combination of guidance and control where we can put it in place. Okay, I've not been able to set it up just yet. So give me a 1 or 2 days time and you should see your assignment go live. Okay, where we'll try to precisely see this guidance algorithm, which is using an LOS, which is driven by an inside PID controller to drive the heading down to zero. Okay, and eventually that should help us achieve path following or trajectory tracking problems. Okay, excellent. Any other queries before I stop? No other queries? All right. Yeah, this will become a little bit more clear once we attack the assignment. So because that is where you'll actually practically see these things come together and it will be much more fun to see that. Okay, all right, let me stop recording here.